Hello, my dear JEE Advanced aspirants. This is the time to think differently because if everybody is thinking the same, how else will you have an extra edge over your competitors? So that's why I bring to you very unique questions. These questions I never discussed on the channel or anywhere else. So you will find, these questions to be not only very unique but also very interesting and will compel you to think very differently. And that is what is needed so that you secure a top-notch rank to get a seat, grab your seat in IIT. Okay, so let's begin with this awesome physics lecture for JEE Advanced 2025. And in the days to come, we'll also have classes for IIT and all the other entrance exams which you are demanding for. Okay, BITSAT, everything. Don't worry. Okay, so time to start. Welcome, my dear students. So please stay subscribed on the channel, or else you will miss all the important classes when we are going to conduct it. You will not get notification because, or else YouTube will not recommend it. So not only subscribe but also like, so that it shows your support for the channel, because this is the channel for all the students in English medium with quality content. All right, so we want all the students to do really well. That's why we are tirelessly working for all of you. Hi Dia, welcome. Hi Dikshita, Viswa, welcome. Alan, hi Lily, hi Shanu, welcome aboard, my dear students. I hope you are doing great and having a great time, my dear students. So time to start with the session. Here comes the first question on your screen. There is a satellite which revolves around a planet in a radius of r much larger than the radius of the planet itself. That means the size of the planet is very small, the radius of the orbit is very huge. Okay, now the time period of revolution is t. If the satellite is stopped and released in the orbit experiencing gravitational force only due to the planet, what will be the fall on the planet for the satellite? Or will it not fall, or will it fall? It cannot fall into the planet, so time of fall is meaningless. Very interesting question. Let's try to understand the situation first. This is just a simple diagram, okay, which has been drawn, and the diagram shows that there is this planet, this is the satellite which is going. So here is what happens, my dear students. If the satellite has some particular speed, which is basically given by root of gm divided by r, then it continues its circular orbit. And the reason why it continues is because the centripetal force is given by the gravitational force, which provides the necessary centripetal acceleration. Usually that is the case. But in a special scenario where the velocity of the satellite itself becomes zero, then the gravitational force is not going to provide the centripetal acceleration. Rather, it is just going to accelerate it normally, and the acceleration will be towards the center of the planet, and eventually you will see that the planet will hit the surface of the the satellite will eventually hit the surface of the planet. So it is going to fall and it will definitely collide. So saying that the fall is meaningless or it will not fall, that is entirely not true. So if you see over here, it cannot fall into the planet. No, this is wrong, guys. It will definitely fall. It will fall into the planet. So C option is correct. So out of these two, did you understand why saying D option is wrong and saying C option is correct? Everyone till this point? Absolutely clear? So definitely that gravitational pull is going to suck that satellite onto that planet and eventually it will fall onto it. But that is just C and D option. Now the question is still incomplete because we have two more options to go, and it says how much time will it take to fall onto the planet. Now this is very interesting. Let's think about it carefully. See, let's just imagine now, this is that planet. Okay, this is basically that particular planet, and the satellite is going around it. In a circular orbit. Let's say it is like this. By Kepler's laws, we know that always the planet will lie at the focus, and the satellite, whatever is there, revolving body, will go in elliptical or circular orbits. So when the speed is exactly equal to root gm by r, then the orbit is definitely circular in nature. Then the orbit is basically circular in nature. Now, just imagine you slowly reduce the speed of that particular satellite. How will the orbit change? From circular, it will definitely become elliptical in nature. From circular, definitely it will become elliptical in nature, something probably like this. Correct? But still, you will notice that the planet is at the foci of that particular ellipse. You reduce the speed even more, it will become even a smaller ellipse, something like this. Maybe. Yeah, it will become even a smaller ellipse. You reduce the speed even further. You reduce the speed even further, my dear students. So it will probably look like this. It will probably look like this. Yeah, slowly it will become like this. But the planet is still at the focus. Eventually, you make it so small. Eventually, you make it so small that it feels as if it is almost going in a straight line. Feels as if it is almost going in a straight line. The ellipse has become thinner till it becomes almost like a straight line. Are you able to visualize this? So first it was circular, then it became elliptical, then it became elliptical, and as you kept on reducing the speed, elliptical, as the speed is reduced, and you kept reducing, the ellipse becomes smaller, thinner, till it becomes almost like a flat ellipse. Now this last one is the most interesting part. Observe it. It's almost it's so flat, it's such a thin ellipse. It's such a thin ellipse that it is approximately feeling like as if it is going in a straight line. The planet is always at the focus. Keep in mind, this is all according to Kepler's law. Kepler's law. Kepler's first law. Now, this is exactly what we want. When we stop the satellite moving around, it goes in a straight line, feels like a flat ellipse where the planet is at one of the focus. So we are interested in basically this situation, and we are going to compare it with the circular situation. Now let's use Kepler's third law to solve it further. Let's use Kepler's third law to solve it further. So as per Kepler's third law, let me put it over here only. Maybe I'll just duplicate this. As per Kepler's third law, as per Kepler's third law, the square of the time period is proportional to the semi-major length of that particular axis, the whole thing raised to 3. T square is proportional to semi-major length raised to the power 3. So if you look at the first scenario, when it is going in a circular orbit, the time period was t. So the square of the time period will be some constant multiplied by the semi-major length of that ellipse. In this case, it is a circle. The semi-major length itself will be the radius. Is that right? The semi-major length, which is also going to be the radius of that particular circle. So it will be k multiplied by just r cube. Now, if you talk about the final situation, when it is a thin ellipse, the entire time taken, let's say it is t2. So t2 square will be some constant into what will be the semi-major length of this particular thin ellipse. This entire thing is the major length. Semi-major length is only this much, where this is r. So this will be nothing but r by 2. So this is nothing but r by 2. So that is the semi-major length. So this will be nothing but r by 2, the whole cube. Now from this, let's just figure out what is the value of T2. Let's just figure out what is the value of T2, because if I divide both of them, what happens is, obviously you will see this k and this k will get cancelled. Even this r cube and this r cube will get cancelled. So I am just left with t square by t2 square is equal to This 1 by 2 will go on the top, so this will become basically t cube. So therefore, t2 square will be t square by 2 cube, which is nothing but 8. So therefore, t2 will be t by root of 8. t2 will be nothing but t by root of 8. This much is clear? Everybody with me? Everybody with me? Let me know quickly in the chat box if you have understood it till this particular point. Everyone, quickly. Yep. So we have figured out how much time does the satellite take to go around once if it was a thin ellipse like this. But here is the catch. Here is the catch. The catch is that this thin ellipse, the total time period of revolution is t2, which is t by root 8. But if it were to just fall, if it were to just fall freely like this, it's just one way of that ellipse, one way of that thin ellipse that you have. Just consider one way of that thin ellipse. That one way is exactly the time duration for that fall onto that planet. So can I just say that the time taken to fall is technically nothing but that t2 divided by 2, t2 divided by 2. Everybody with me? t2, whatever we got, divided by 2. Everybody understands this? Absolutely clear? Very good. So just take the value of t2, which was nothing but t by root of 8, and then divide it with the number 2. That's it. Divide it with the number 2. So that's it. So this is nothing but 2 comes over here. Root of 8 is nothing but 2 root 2. So this is nothing but t by 4 root 2. So that is the time taken to fall. That is the time taken to fall, which is t by 4 root 2. Is this clear, my dear students? So very interesting, unique problem. As you can see, the time taken to fall is nearly t by root 8. No, time taken to fall is root 2 t by 8. Now, if you want to write it in a slightly different form, let's see. This will be root 2 into t. 8 is nothing but 4 into 2. 4 into 2. So basically this will be root 2 into t. That root 2 will cancel. So this will become t by 4 root 2. Oh, exactly, this is what we need. So B is the right answer. A is obviously wrong. A is obviously wrong. B is the right answer. We just figured it out right over here. T by 4 root 2. That is the time taken to fall. So the concept involved here was Kepler's first law as well as the third law. The first law talked about the orbits and how the semi-major length will be. And the third law gave me a calculation for the time period of revolution. So as I made the ellipse smaller and smaller, the time period will change. But the flattest ellipse time period will be the time taken to go till the planet and come back. So just we wanted the time to go one way. So we just divided the time period of revolution by half. So that's it. I will get the answer then. Is this clear? Let's go ahead to the next question, my dear students. Beautiful question. Welcome, country. All right. Okay. Very good, Vivid. Very good, Panaru. Very good, Faisal. Awesome. 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 Let's go, guys. Next question coming up on your screen now. A tablecloth of certain length is lying on the table. The length is L from here to here, the dark white line that you see. The edge of the cloth is at the edge of the table. You can see the edge of the cloth is at the edge of the table. This is the table on which the cloth is lying. There is a block which is kept at the center of the tablecloth. You can see this particular block exactly midway. So L by 2 from here, L by 2 from here. A man pulls the end of the tablecloth horizontally so as to take it off the table. You might have heard about this example back in your school days where you display the concept of inertia, the concept of mass. You pull the cloth, the block stays there almost, okay? And you would have learned the concept of inertia via this example back in your science textbooks. Okay, so the person is pulling the block horizontally so as to take it off the table. But think about it, when you start pulling it off, yes, the block has inertia. It won't exactly stay there because the block and the cloth surface together have some friction between them. So I think the block will be slightly dragged in the front. If you pull it out slowly, then the block will fall off the table. But if you pull it fast enough, then the block might not fall off the table. It will probably land here or here or here somewhere, depending on your speed. So if the cloth is pulled at a constant speed, then the coefficient of friction between the cloth and the block, how much should it be so that it does not fall off the edge as the cloth is pulled out? See, I'm pulling it out. If the friction is very large, what will happen? Then this block will easily get pulled off the edge. It will probably get pulled off the edge and it might fall off over here. But if the friction is too less, imagine zero, then the block will not move only. You can easily pull out the cloth, the block will just fall here. So I want to strike a balance where I want to find that maximum friction which can exist, so that even when I'm pulling that cloth out, the block might probably go here, might go here, might go here, might go till here, but it can't reach beyond the table's edge. So that is the concept over here. So the question is on the coefficient of friction, if I'm not wrong. And yes, they have just asked the coefficient of friction. Options are not given. Okay, maybe it can be a numeric question or paragraph question where you have to figure out the final answer and then mark it properly. All right, so let's think. Okay, so expression will come in terms of given quantities like V naught, G might be there. Okay, some length might be there. All these things might come up in the final expression. Let us see what we can do. Well, first things first, that table is over here. This is your table. The cloth which is there, right now over here, you are pulling it with a constant speed of V naught. This length is L. So this end to reach here, because this is constant, can I say the time taken, let's say if it is T, time and speed, right, and distance. So how do I relate them? We can just say V naught is distance divided by time. So therefore time is nothing but L divided by V naught. That's it. So this is nothing but speed is distance by time. Distance covered is L. This end will move from here to here. Okay, it will start from here. It will reach eventually at this point. So distance covered is L, time taken is T. So speed is distance by time. Very simple. Speed is constant. This is the first equation which I can think of. Okay. Now what next? What next? See, this block is definitely going to move from here to here. And in the most extreme case, what will happen is, in the most extreme case, here is what will happen. Observe this carefully. In the most extreme case, this cloth, when it is pulled out almost from that particular table, probably something like this. Okay. So your block was here. Probably your block would have just reached over here. In the most critical situation, your block has just reached over here. And after this, the cloth will go beneath its surface and the block will topple over on the edge. That is the most extreme scenario. Beyond this, nothing else can happen. If the friction is less, the block won't even move this much. So tell me one thing, how much do you think the block has moved? How much do you think from this situation to this situation the block has moved? Come on, think about it. From this situation to this situation, how much has the block moved? The block was exactly at the center. It has gone till here. So 100%, this particular block has moved only this much. And this particular distance is none other than L by 2. It is nothing but L by 2. Is that right? It is nothing but half the length of the cloth. But why was it able to move in the first place? Think about it. Why was it able to move and reach over here in the first place? Think about it. Because of the friction acting beneath it. Remember, there was friction below it which was dragging it. So that friction was nothing but mu into n, which is nothing but mu into mg. This was dragging the this was dragging the block. This was dragging the block from the initial situation. Okay. So because of which the block would have definitely have had some acceleration, which I can write it as A. So I think we can find out acceleration. So how much is that acceleration? Because no other force is there. So using Newton's law of motion, we can say that the friction is mass times acceleration. So therefore, mu mg is m into a. Therefore, acceleration is mu into g. This acceleration has caused some displacement starting from rest. So I think we can use kinematics now. And the kinematic equation that will be most useful is S is ut plus half at square, because I do not know what speed does it have over here. So the displacement that it undergoes is nothing but L by 2. Initial speed was 0. Acceleration that it has is nothing but mu into g. So I'll put mu into g over here, and over here t square, and over here t square. Now what is the value of t that you are going to put, my dear students? What is the value of t that you are going to put? Exactly this time, because by the time the cloth's end will reach here, the time would have elapsed is exactly this much. So I will put the time as L divided by V naught. That's it, the whole square. Okay, let's see what happens next. So I will have L by 2 over here. I will have mu g L square divided by 2 V naught square. L cancels, 2 also cancels. So therefore, I am left with nothing but 1 is equal to mu GL divided by V naught square, but I wanted mu. So mu will be nothing but take V naught square on the top, divided by GL. So V naught square by GL is the bare minimum, or is the maximum friction which you can have, beyond which you will see if the friction is existent, then the block will topple over. So I will say that the value of mu must be more than 0 or equal to 0, and should be less than or equal to V naught square by GL, so that the block falls on the table, and it does not fall off the table. So the block will always land on the table, it will not fall off the table. So only then it will work. Is this clear? So beautiful question, very interesting question. So the answer is less than V naught square by GL. Less than V naught square by GL. Very, very, very different question. You have seen this experiment so many times back in the day at school level. So this time you are seeing it as a numerical problem with friction involved, coefficient, and all of these things. Okay, so let's move to the next question. I hope you are enjoying the session, and if you have forgotten at this point of time to smash the like button, please reminding you to smash that like button, and also stay subscribed on the Vedantu JEE English channel. Okay, because it takes a lot of effort to give you such quality questions, right? So please support the channel. Two uniform spheres are shown over here. They are rotating separately on two parallel horizontal axes passing through their centers. The upper sphere has an angular speed omega naught, and the lower sphere is at rest. Now the two spheres are moved together so that their surfaces will touch. After a short time, both of them are in contact, are rotating without slipping. Find the rate of rotation of the upper sphere in radians per second. Moment of inertia is everything, blah blah blah. Speeds are given, initial speeds, etc. And radius are also given. Okay, let's understand what is exactly happening over here. It's a very different question, and a lot of people are going to jump onto angular momentum conservation. So this is one sphere. Think of this as the axis. It is rotating like this. Zoop. It is rotating like this. This is another stationary sphere. Right now it is not doing anything. The upper sphere is rotating, rotating, rotating. Slowly it is brought in contact with the lower sphere. The moment it is brought in contact, both of them will start slipping and eventually they will begin to rotate. Eventually they will begin to rotate and they will achieve some speed and they will no longer slip, and you will see the speeds will not change after that. So there is some transfer of energy from here to here. There is also some loss of energy because there will be some slipping. So first things first, whatever will happen, let me tell you. Uh, what is not conserved? Energy. Energy is not conserved. Energy is not conserved. And the reason for that is as friction during the slip, during, as the friction during the slip causes some loss, causes losses of energy, causes some losses. So energy is definitely not conserved. Energy is not conserved. So the next situation or the next law that you might think of is angular momentum conservation. Angular momentum conservation. What about angular, because this looks like a problem of angular momentum conservation. You have solved many problems like that. A disk is rotating, it is placed on another disk, it slips initially and eventually they achieve a common angular speed. But that problem is different from this problem slightly. Angular momentum conservation. What do you think about it? Angular momentum conservation principle demands that the net torque be zero. So if you take any point, let's say for example this point, understand that there will be torque because this axis which is rotating, might experience some kind of force, because imagine both these spheres are rotating when they are touching each other, so that axis will try to move left, right, or front or back. So there will be some force. That force will create a torque about this point. So torque is there, so angular momentum is not conserved. If you take this point, then even this axis will try to move front or back because of the friction. It will try to move in the front or back. So there will be a normal on the sphere. So there will be a force and there will be again a torque. So no matter where you go, if you go here also in just in between the point of contact, both the spheres where they touch, even there friction might not give any torque, but there is a normal force acting by the axis on this guy, also a normal force acting on this guy. Both these normals will give torque. So definitely angular momentum cannot be conserved. So angular momentum is not conserved, is not conserved, very very important, as net torque is non-zero, is non-zero. No matter where you go, torque is always going to be there. So you can't use energy conservation, you can't use angular momentum conservation. So you are in a bit of a soup out here, because none of the usual laws which helped you are solving the problem. Understand that. So we have to think a little bit differently, my dear students. Look at this diagram from the side way. It looks much easier. Yes, look at it from the sideways. It will look much easier. So this sphere is over here and maybe this sphere is over here. The radii are different. Please keep that in mind. Yeah. So let's say this has a radius of A, this has a radius of B. So you can see now why when they touch each other, there will be friction between them. There on this guy, let's say the friction is this way. On this guy, the friction will be the other way. So that friction is going to create that torque. And also at this particular point, there will be a normal, let's say like this. I call it N2. Let's say there is a normal like this. Let's say I call it N1. So always there is a torque no matter which point you go. So you cannot really say that I can conserve angular momentum. So maybe this was rotating like this, and maybe this was rotating like this. It starts to rotate. This was at rest. It begins to rotate. So initial speed is omega. Final speed is omega 1. This is, let's say, omega 2. This is omega 1. This is omega 2. This is the final situation once they touch each other. Okay. And after they achieve a common speed, you will see that there will be no slipping and the friction will also go away. So this is very important to mention. When omega 1 and omega 2 become constant with time, basically they become steady, then there is no slipping which occurs. So that means there will be no friction anymore. There will be no friction which will act anymore. And because there is no slip, that means the relative velocity of the point of contact is zero. So the relative velocity of the point of contact is zero. Relative velocity of point of contact is zero. So velocity of sphere A is velocity of sphere B. So this particular point and this particular point both have the same velocities. Just visualize this. Just visualize this. This point on sphere A and this point on sphere B, both of them have the same speed. So the relative speed is zero. So that's why there is no slipping between the points. VA is omega r, VB is omega r again, but the radius are different. So omega 1A is equal to omega 2B. Lot of people made a mistake saying omega 1 is equal to omega 2. Definitely not correct. Their linear speeds at the point of contact are same. Angular speeds will be different because the radii are different. Is this absolutely clear? Okay. Perfecto till this point. Okay. Yes, sir. Till this point, everything is clear, sir. Now, what do you do next, sir? Tell me. Okay, I will tell you. Let's figure out. I'm just putting it on a separate page. Maybe we'll need more space. That's the reason. This is one equation. I don't know omega 1. I don't know omega 2. I just know initial angular speed was 12 radians per second. I think the printing is not right. This was supposed to be omega, guys. So initial omega was 12 radians per second. Okay. So what do we do next? When angular momentum has failed us and energy conservation has failed us, then there is only one thing which can help us, and that is Newton's law and impulse, basically. And remember, impulse in linear translation motion was change in momentum, which was force into time. But here, it's not a linear mechanics, it is rotational mechanics. So you have to convert everything into angular terms. So instead of force, you will use torque. Instead of angular velocity, you will use, instead of linear velocity, you will use angular velocity. Instead of linear momentum, you will use angular momentum. So the term which we should use instead of impulse is angular impulse. And it will be torque into time. And it will be also change in the angular momentum. So realize this, the same friction acts on, the friction force acts on both the spheres for same time. Let's say I assume the time to be t. So therefore, think about it. What can I say? That there will be some angular impulse. There will be some angular impulse due to the frictional torque. Due to the frictional torque, and we know that the torque is nothing but torque multiplied by the time is nothing but the change in angular momentum, and torque, we all know it is nothing but R multiplied by the force. So I will write this equation for angular impulse is change in angular momentum, once for this sphere and the second time for this sphere. And let's see what do we get exactly. Okay. So for the first sphere, the radius is nothing but A. The force of friction is nothing but F. The time for which it acts is nothing but T. Is the change in the angular momentum. So it is nothing but going to be I. Okay, this is going to be I. Oh, by the way, the final angular momentum will be less. Initial angular momentum will be more. So to keep it positive, I will write it as I omega 1, I1 omega 1 minus I1 omega whatever was there initial. I just want to keep it positive, or else I have to put a minus sign and then put final first and then initial later on and all of that. So to keep it positive, the radius multiplied by the force multiplied by the time is change in angular momentum. So I1 omega 1 minus I omega, but we know that initial angular momentum was more, so that's why I will put I1 omega first and then I will put I1 omega 1. Is this clear? Because I know this is higher, eventually it will become lower because it will rub against it, the speed will become less, just so that this number stays positive. That's the only concern, or else I have to put mod and all of that. I want to avoid all these things. Next, for this guy, the radius is nothing but b, the force of friction is F, the time taken is t, final angular momentum is I2 omega 2. Initially it had no angular momentum at all. Oh, from these two I got a very good idea what I should be doing. Maybe the best thing to do is to divide both of them. Yes, just divide both of them and see what do you exactly get. FFTT gets cancelled. So A divided by B is nothing but I1 omega minus I1 omega 1 whole thing divided by I2 omega 2. So therefore I can just say A divided by B is nothing but I1 is common, omega minus omega 1 whole thing divided by I2 omega 2. Is that right, everyone? Till this point, absolutely clear? Everybody absolutely clear, my dear students? Very good. Now, what is the next thing that we should be doing? What is the next thing that we should be doing? Think about it. If you observe carefully, what is the question? The question says, find the final rate of rotations of the upper sphere. Upper sphere, that means we have to find omega 1, that means we have to get rid of omega 2. So, write what is omega 2 from here. Omega 2 will be B goes on the top, A comes below, I1 goes on the top, I2 comes below, omega minus omega 1. That is what omega 2 will be. When it goes on the top, B goes on the top, A comes below, I1 by I2 is there, omega minus omega 1. Take this omega 2 and just substitute it over here. That's it. So therefore, what I will get is, therefore, omega 1 A divided by B, which is supposed to be omega 2. Instead of omega 2, I will write this whole thing, which is B by A, which is nothing but B divided by A, I1 by I2, I1 by I2, and we have omega minus omega 1, omega minus omega 1. All right. So now it's just a matter of rearranging everything. But before that, let me take B by A on the top and I2 by I1 also on the top. So let's see what do we get. So omega 1 A square divided by B square into I2 divided by I1 over here is omega minus omega 1. So bringing omega 1 together, omega 1 1 plus A square by B square I2 by I1 is equal to omega. Therefore, omega 1 will be omega whole thing divided by 1 plus A square by B square I2 by I1. That's it. This is the final answer. This is the final answer. Is this absolutely clear, my dear students? Is this absolutely clear? Now it's just about substituting all the things in this particular equation. What is the initial angular speed? Initial angular speed is basically 12. So just put 12 over here. 1 plus A by B. What is A and what is B? A is 2, B is 1. A is 2, B is 1. A is 2, B is 1. That's it. What is I2 and I1? What is I2? I2 is 2, I1 is 4. I2 is 2, I1 is 4. I2 is 2, I1 is 4. That's it. Solve this and see what is the answer that you are getting. Come on, solve this, my dear students, quickly and tell me what is the answer that you are getting. Yep. 2 square is 4. This 4 and this 4 will just cancel out. So I will be left with 12 divided by 1 plus 2. 1 plus 2 is 3. 12 divided by 3 is nothing but 4. So the answer should be 4 radians per second. Let's see whether this is actually correct or wrong. Okay. Yes, the answer is 4 radians per second. Perfect. We have solved it. So the beauty of this question, and which compelled you to think differently, was everything over here. Energy is not conserved because initially when you bring them in contact, they will start slipping until the slipping goes away when they move together. So energy is not conserved because friction will cause heat losses. Angular momentum is not conserved because looking at the free body diagram itself shows you why the normal reactions will give some torque no matter which point you take. And the essential condition for conservation of angular momentum is no torque should be there on the entire system. So that is also not conserved. So we went along with angular impulse is change in angular momentum. Angular impulse means instead of force into time, we use torque into time. And torque is R into force. So R into force into time is angular impulse, which is change in the angular momentum. So the moment you do that, everything falls into place. Very good, Raghu. Awesome. Okay, where did I learn my physics from? Oh my God, there is that will take an entire lecture in itself. Okay, so to tell you about it. But nevertheless, I will tell you someday. It's not such an easy answer. Okay, next question. There is a uniform magnetic field in a circular region of radius r whose magnitude changes at the rate of dB by dt. The EMF induced across the ends of a circular conducting arc of radius r1 having an angle OAO. OAO. So I think this angle, let's assume it to be theta, is how much? Very interesting question. Okay. Now the magnetic field is only there in this region, but the conducting arc is outside that region. How much is the EMF induced? So I'll tell you something. If you use Faraday's law and had there been a complete loop, something like this. If there was a complete loop, then the EMF induced in that entire loop magnitude wise will be the rate of change of flux within that loop, but the flux is only changing in this much area, so it will be nothing but d by dt, and there will be obviously magnetic field into area which is there inside. That area is nothing but pi r square. Think about it. Only this much part, only in this much part, the magnetic field is there, and that is where the flux is also involved and it is changing. So only that much area should be considered for calculating the flux, and rest of it will be as it is your, dB by dt. So that is the EMF in that entire loop. Now that loop is made of 360 degrees or 2 pi radians. So think like this. For 2 pi radians, the EMF induced is nothing but your pi r square, multiplied by dB by dt, pi r square dB by dt. So now think about it. What will be the EMF which will be created only in an angle, only in this particular angle? Where is it? Right over here. Just from here to here. Only in this particular angle. If you just consider this much part of that, okay, then for theta radian, what will be the EMF induced? Obviously, it will be theta divided by 2 pi, and then you will have all these things as it is, pi r square multiplied by dB by dt. Now we can all see that pi gets cancelled, so therefore it will be nothing but theta r square divided by 2 multiplied by dB by dt. So that should be the answer. For 2 pi radians, it was this much. For theta radians, how much will it be? Unitary method. So theta r square by 2 dB by dt. Theta r square, where is it? Theta r square, uh, yeah, theta r square dB by dt, and this whole thing divided by 2. Is this absolutely clear, my dear students? Perfect. Yes. So the correct answer is option labeled C. Theta r square dB by dt divided by 2. Yep. Right over here. Very straightforward. You had to just use unitary method. Okay. Cool. Let's go to the next question coming up on your screen. The thermodynamic system is taken through a cyclic process, C to D, D to E, E to C. The question is, what is the efficiency of the cycle? The gas is helium. Okay, let's understand how to solve this particular question. First of all, let's understand the meaning of the word efficiency. Okay, let's understand the meaning of the word efficiency. So the efficiency, usually the symbol is eta, is nothing but how much are you getting, which is the output, divided by the input, multiplied by 100 if you want it in percentage. Okay, as we can see in this particular cycle, the output, because it's a clockwise cycle, whenever the cycles of pressure volume diagrams are clockwise, it is going to be an engine. When it is anti-clockwise, it is a refrigerator. So keep this particular thing in mind. If it is clockwise in the PV diagram, it is going to be an engine. Whereas if it is going to be anti-clockwise, it is the reverse of an engine, which is called as a refrigerator or a heat pump. Refrigerator or a heat pump. Usually the word used for refrigerator, the performance of coefficient, that is what you will calculate. For engines, it is usually the efficiency that you will be calculating. So for an engine, the output is how much work you are able to do upon how much heat has been absorbed. Depending on how much heat is absorbed versus the work done, that is how you will be able to calculate the efficiency of it. So I just need to say how much is the work, how much is the heat, and then my job is done. We will get the efficiency in the next few lines. Is this much absolutely clear? So why clockwise is engine? Because when it is clockwise, work done is positive. That means it will do work. An engine is supposed to do work. Refrigerator, you do work on it, because anti-clockwise means negative work done. So then the work will be done on it and it will absorb the heat from this. Yeah, correct. So now what we will do is, let's calculate the work done and heat absorbed. Calculation of work done is very simple. See, the calculation of the work done in that entire cycle is nothing but the area which has been enclosed, in the pressure versus volume graph, in the pressure versus volume diagram. So this is nothing but a triangle. So the height multiplied by the base, which is this much, into half. So what is the height? The height is 400 minus 100, which is basically 300, and the base 2 and 4. So obviously it is going to be 2. So 2 cancels. So it is nothing but 300 joules. So that is the work done in that entire cycle. So first of all, I'll put 300 over here. So only thing remaining is heat absorbed now. Now let's think carefully. In every step, whether heat is absorbed or actually released, because if it is released, don't count it. If it is absorbed, only then count it. I have seen many students saying, sir, Q is equal to W in a heat cycle, so then you will just substitute heat absorbed as 300, then the efficiency will become 100%. No, don't take the total heat, only the places where heat is actually absorbed, not where heat is released. So if you go from E to C, if you start taking one by one in this particular region, okay, let's see, in the region from E to C, what exactly is happening? It's a isobaric process, because pressure is definitely a constant. Pressure is definitely a constant. Can you see that? Yes. So heat absorbed or released will be given by Q from E to C will be N Cp delta T. Now this is very interesting. Delta T, guys. This point versus this point, who has higher temperature? Just think about the isotherms. Just think about the isotherms, my dear students. The isotherms, the isotherms, the isotherms. The isotherms will go like this. This is at a higher temperature. This is at a higher temperature versus this one is going to be at a lower temperature. So you're going from high temperature to low temperature. That means this delta T will be negative. That means this heat will also be negative. That means it is not absorbing it, it is releasing it. It is releasing it. So do not count it. Do not count the heat which is involved from E to C. Everybody till this point? Absolutely clear? Okay. Next, let's go from C to D. Let us go from this line, point C to point D. This is a process which is definitely isochoric. The volume is constant. So the heat which will be involved from C to D will be given by NCV delta T. Okay, what is CV? Clearly mentioned somewhere. The gas is helium. What does this tell you? The gas is helium. It is a monoatomic gas. CV for it will be 3R by 2 and CP for it will be 5R by 2 because the degrees of freedom will be 3. 3 degrees of freedom will be there. So 3R by 2 and 5R by 2. So let's put the value of CV over here, which is just going to be 3R by 2 into delta T. Okay, I have an idea now. So 3 by 2 moles are not given. I'll just put NR delta T over here. So think about it. What is NR delta T? NR delta T will be either P delta V or V delta P. In this case, using gas law equation, it will be nothing but V delta P. This is just using our gas law equation. Since PV is equal to nRT, so V delta P will be nR delta T. Okay, this much understanding you will have. Please don't ask me to explain this step now. Okay, I'm just taking the difference of the gas law equations. Okay, so what is V delta P now? Volume is basically 2. What is delta P? Final pressure minus initial pressure, that means 400 minus 100. Okay, 2 cancelled, so 3 into 400 minus 100 is basically 300. So this will be nothing but 900 joules. This will be nothing but 900 joules. Everybody till this point absolutely clear? Everybody till this point absolutely clear, my dear warriors? And this is positive. Since this is positive, that means it has definitely absorbed in this part. It has definitely absorbed in this part. Now, in this part, whether the temperature has increased or decreased, I do not really know. So I have an idea just to compare the temperatures between D and E. Between D and E, it is neither isobaric, isochoric, isothermal, adiabatic, nothing it is some different process. Just compare the temperatures. How? See guys, PD, VD will be nRTD and PE, VE will be nRTE. So now divide both of them. Okay, take both of them and divide both of them. So if I divide both of them, PD, VD divided by PE, VE will be TD by TE. Okay, what is PD and what is VD? PD is nothing but 400. VD is nothing but 2 divided by PE. Pressure at E is 100. Volume is basically 4. Is TD by TE over here. Okay. So what do I really get? This is nothing but 800. This is nothing but 400. So this is 800. This is nothing but 400. So this is 2 by 1 is TD by TE. That means temperature of E is less, temperature of D is more. So the temperature of E being less, that means heat is being lost. So heat is basically not absorbed, it is lost. It will be basically negative in a way. It will be definitely negative because the temperature has reduced. Everybody till this point absolutely clear? Okay. So in this entire cycle, there was only one place where heat was absorbed. Even here, the heat was not absorbed, it was released. So the only place where you should count is over here between C to D, which was nothing but 900. So this is nothing but 900. Everybody till this point absolutely clear? So this is going to be nothing but 1 by 3 multiplied by 100%. So this is nothing but going to be 33.3%. 33.3%. So I think none of the options are matching. Maybe one of the options had to change. Maybe I'll change some of the option so that it matches then. Maybe I'll change this option. Yeah. 33%. So the correct answer to this question is 33%. Is this absolutely clear how we solve this question? Find out the work done separately, find out the heat absorbed separately, and then solve the question. Okay, beautiful, beautiful question, my dear students. Moving on to the next question coming up on your screen. There is a triangular wire frame which is made and the length of each wire is L, mass is M. The whole system is suspended from a point O. This is a triangular frame and it is free to oscillate, and it is having a time period T1 when the axis is x-axis, and it has a time period T2 when the axis is z-axis, which is coming out of the plane. Then choose the correct option. Compare the time periods. Beautiful question. Let's see. Okay. Now, see, first time the axis is x-axis, next time the axis is y-axis. So, understand the difference in both the cases. In the first case, this is it. This is your x-axis along which it is oscillating, like this. And in the second case, the axis is basically towards you and it is oscillating like this. In the wire frame, let me show it over here. That's it. Okay, these are the two situations. This is second situation, z-axis. This is the first situation, this is x-axis. Okay. In both the cases, the center of mass is at the same distance. And remember the usual formula for time period. The usual formula for time period is 2 pi under root moment of inertia by mass into g into d. Where is the center of mass? Exactly over here. The center of mass is over here. So technically this distance will be d, whether you rotate it like this or like that. The distance from the axis is d only, mass is same, g is same, 2 pi is a constant. So basically it is a comparison of moment of inertia now. So essentially I can say time period is directly proportional to root of inertia because d, m and g are basically the same in both the cases. The mass, the distance from the axis and the acceleration due to gravity, all of them are same. Hi Pranav, good afternoon. Hi Nikita, good afternoon everyone. How to manage PYQ and PYP? What is PYP, man? This is some new term. Please explain the new terms because somewhere and all you will find these terms. Please explain, guys. I'm little old, I feel now. Okay. See, I'll tell you what. How do I compare the moment of inertia? So I'll just give you a hint because anyways, this is the last question. Okay, you think about it. When I rotate it like this, consider these two rods. Which rods am I saying? This rod number 1 and rod number 2. Both of them have the same moment of inertia. Both of them have the same moment of inertia. Okay. Now, when you rotate this rod like this versus consider this situation, consider this rod 1 and 2. This is the axis. This is your rod and you're rotating about this axis. When you rotate it like that, the moment of inertia is ml square by 3 about the end. Remember, moment of inertia about the end of the rod is ml square by 3. This moment of inertia, notice you're not rotating the rod like this, but rather it is at an angle and you're rotating it like this. It's way different, guys, than rotating it completely like that versus like a conical pendulum. Yep, this is like a conical pendulum, my dear students. This is like a conical pendulum. 100% the moment of inertia is going to be lesser than your ml square by 3 because all the masses are closer to the axis versus here this mass is going in a big circle. Check that out. All the masses are going in big circles like this. All the masses are going in big circles like this versus all the masses are close to the axis. So moment of inertia for both the rods 1 and 2 is definitely less in this situation as compared to the same rods in this situation. Now what about the third rod? What about the third rod here and over here? Just think about it. In this situation, this rod is going like this. This rod is flat and it is just sliding like this. All the masses are going in a big circle of this radius. Whereas over here, this mass is going like that. Now observe this carefully, guys. This is very interesting if you think carefully. Here, this particular rod number 3 we are talking about, this distance is the same as compared to, in this situation, this particular distance. Okay, this distance is the same. Whatever this distance, let's say this distance is x, this is also going to be the x. But the manner in which they move is way different, guys. In this situation, because the axis is x-axis, think about it. It is going in a circular path like this. It is going in a circular path like this. Just visualize this. Just visualize this, my dear students. It is going in a circular path like this. All the masses are at distance x only. Whereas over here, because the axis is the z-axis, this is your axis. All these things will go in a circle like that. Meaning this point, think about it, this point will go in a circle like this. Whereas these points are little bit farther apart and they will go in a bigger circle. So they will have more moment of inertia because of more distance. Everyone over here, they will have more moment of inertia because they are going in bigger circles, definitely. So 100% this situation, rod 1 and 2 has more moment of inertia as compared to these rods. Even the third rod has more moment of inertia because all these masses are going in bigger circles as compared to the center of the rod. Whereas here all the masses are going in the same radius. Here all have same moment of inertia. All the points have same moment of inertia, same radius. So definitely this guy's moment of inertia, which is basically I2, is definitely going to be more than I1. So if I2 is more than I1, what can you say about T1 and T2? Obviously, T2 will be more than your T1. That is the direct result which will follow using this law, using this particular law. Which one? This one. That's it. So T2 will be more than T1. T2 will be more than T1. It's a very interesting problem where you don't sit and calculate. I have seen many teachers actually sit and calculate the moment of inertia. No need of it. You have to use your logical brain and immediately you will get the answer without one equation also. I have not written one equation throughout the problem. Just by pure analysis, we have got it. It's a beautiful question, my dear students. And that was the last question. So I'll be sharing the PDF, and if you want more of these classes which will compel you to think differently, very unique questions, please comment below. Yes, sir, we need to think differently, or think different, more sessions needed, and smash that like button as well. Okay, I'll bring in more classes for all of you. Just leave a comment. Thank you so much. Thank you for liking. Bye bye. Take care.